Okay, so Unit 6, continuity. Okay, so in Unit 5 we saw limits of functions that are the behavior of a function when it gets close to one particular value, right? There are some types of functions in which the limit of the function when it gets to a point is exactly the value of the function at that point, and that's continuous functions, okay, which are in an intuitive sense those functions that you can draw, with without getting the pencil out of the paper, okay, or the chalk out of the blackboard, right? This is a very intuitive sense that is formalized by these concepts that we will see now. Continuous functions are super important in analysis and calculus in general. Most of the things that we will do will deal with continuous functions, and they have a lot of interesting properties that allow us to say many more things. Okay. So the definition of continuity, or a function that's continuous, a function f is continuous at a point a in the domain if the limit when x goes to a of f of x is f of a, okay, what I just said. And this definition can be restricted to intervals, to subsets of the domain, okay? A function doesn't have to be domain continuous in all of its domain. It could be continuous in only intervals, okay? So it could be that f is continuous in this interval open a b if it's continuous for every point of x in that interval, okay? That equality, the limit when x goes to a of f of x equals f of a, is valid for every point in this domain, right? So and that's also true for all these different intervals, right? Examples of continuous functions are polynomials, as we saw in last video. The limit when x goes to a of a polynomial is the value of the polynomial at a. Rational functions, right? Whenever the denominator is not zero, okay, so in their domain they're continuous. As we saw also, the sine of x and the cosine of x are also continuous. The tangent of x, because it's a fraction of continuous functions, it's also continuous, except when it's not defined, right? Except in the parts or the multiples of pi over 2, where it's an asymptote, right? Also with a cotangent. Okay, so let's see a proof of some other continuity functions. So let's see that the exponential e to the x is a continuous function. Okay, so in order to do that, we have to prove that the limit when x goes to a of e to the x is e to the a. Is this true? Well, we can always write e to the x as e to the x and then multiply by e to the a, e to the minus a, right? Or in other words, we can say this is e to the a times e to the x minus a, right? Now if we compute the limit when x goes to a of e to the x, this is the same as the limit when x goes to a of this expression, e to the a times e to the x minus a, and so this is e to the a times the limit when x goes to a of e to the x minus a. Now we know that this thing is equal, e to the x minus a minus 1 is asymptotically equivalent to x minus a whenever x minus a is small. So in other words, this is wait a minute. Yeah, so this is asymptotically equivalent to this 1 plus x minus a, right? So we can substitute here. We have let's see, this is e to the a times the limit of this expression when x goes to a, so this is times 1 plus a minus a, and this cancel out. This is 1, so this is e to the a, which is what we wanted to prove. So that means that the exponential function is continuous. Okay.